All right, let's begin. Now, as always, if you can hear me all right, I want you to raise your hand. Okay, good. Um, I understand that you're able to listen to me all right. So you can go ahead and lower your hand. So we'll continue from where we left off in the last class. Let's quickly review what we did in the last class. We were talking about memories. All right. So basically, in the memory hierarchy, there's volatile memory and there's non-volatile memory. Okay, volatile memory loses contents when the power is turned off. Non-volatile memory storage is more permanent. Even between power off and on cycles, the contents of memory um, are not overwritten. Okay, and then when it comes to memory, there are two major considerations that we pay attention to. We organize the whole spectrum of memory in terms of um, the writability, how easy it is to write, okay, shown along the x-axis here, and then storage permanence, shown along the y-axis here, okay, and then we know where different memories fall in this hierarchy. That's what we did in the last class. On one extreme is the SRAM, okay, which is very, very volatile, okay, and on the other extreme is mask programmed ROM, which stores its data permanently, but it is very, very difficult to program. It scores very few points in terms of writability. The ideal memory, on the other hand, is something that is extremely easy to write and rewrite, and something that holds data for the lifetime of the product. A permanent, easy to write, rewrite memory is ideal memory. Okay, and then we went on to talk about different metrics here in terms of a high end of writability, uh, low end of storage permanence, so on and so forth. Okay, this is what we discussed in the last class. Then I showed you a technique, okay, where a 4 by 4 memory array can be used as a lookup table. Okay, and I'm going to elaborate on that today. We'll continue the discussion really quickly today. But then this memory cell itself, this guy, this one cell itself, it could be SRAM, it could be DRAM, it could be fuse, anti-fuse technology, so on and so forth. What technology we use to store one bit of data into this memory cell that characterizes the overall memory architecture. If you remember, there is just one repeating cell, right? There is one cell that repeats over and over and over again. That's the underlying idea of memory. This is repeated a billion times if you're interested in 1 GB of memory, so on and so forth. Okay, so that's the idea. We looked at the support circuitry necessary to be able to write to and read from memory. The address lines or the horizontal lines, the data lines or the vertical lines. And then there are control signals, output enable, chip select, and write enable. We looked at all of these. There can be different topologies of memories, meaning there could be different aspect ratios. The same 64 KB of memory could be 64 by 1, 32 by 2, so on and so forth. Okay. And then we looked at the functioning of the different control signals. Then we talked about the advantages, disadvantages of the entire spectrum of memories, SRAM, DRAM, flash, so on and so forth. We looked at the comparison table in terms of read speed, write speed, volatility, density, power, and rewrite. And we looked at the different kinds of memories, ROM memory, okay? What technology, like I mentioned, what technology you use, that decides the kind of memory. In ROM memory, which is permanent, read-only memory, we use fuse technology. So in order to store a 1 or 0, we leave a fuse intact or blow up the fuse in order to store a 1 or 0 respectively. So we talked about all of this in the last class, right? So this is what we did. And then we talked about mask programmed ROM, one-time programmed ROM. I did not spend a lot of time on this, but I invited you to read through this information here, which is mostly relevant theory. Okay, so when it comes to EPROMs, it was the case that you had to physically take your memory chip out of your breadboard, plug it into a positively medievally looking device, programming device that looked like this, then program it and put it back into your breadboard. So the idea is in-system programmability was not available in good old days. Okay, and when I say good old days, I mean for educational purposes in 2006, I was a TA for basic digital logic design course. Okay, and then I pretty much used technology that is pretty similar to this. It looks pretty outdated now, but it was not too far ago. It was not too long back in the past that we use technology like this. Okay, that should speak to the speed at which our technologies evolve. Okay, now we are talking about FPGAs, flash memories, which can be easily programmed and reprogrammed in system. You don't have to take them out of your PCB or breadboard to plug them into special programming devices like this. Okay, then electrically erasable programmable ROM, flash, so on and so forth. Okay, we use flash frequently for embedded system applications. If you took 187, the microcontroller code is stored in the flash memory and data is stored in the RAM memory. So code is stored in flash memory while data is stored in RAM memory. Okay, so this is an example 187. 187 is just one example. So flash is non-volatile and RAM is volatile. Okay, so that's the idea. So all of this we did in the last class. Okay, and then we came to the topic of random access memory. And even within random access memory, I mentioned there are two kinds. RAM has two kinds, static RAM and dynamic RAM. And we are going to take a closer look at these. So now take a cursory look at these two. The one on the top is the static RAM. The one on the bottom is the dynamic RAM. So I have a question for you. Between the SRAM and DRAM, which one do you think has higher density, and why is that the case? Volunteers?
What was density in this context? I don't remember.
Very good question. The density is how many bits you can store in 1 millimeter squared. So in other words, if I'm using, that's a very good question to ask. Now, I'm using 1, 2, 3, 4, 5, 6 transistors to store 1 bit of information. So this must be occupying a large area to store 1 bit. Okay. Now look at this guy, the DRAM. The DRAM is using 1 MOSFET and 1 capacitor. So mostly in the order of 2 transistors to hold 1 bit of data. So it must be using lower amount of area to store 1 bit of information. So with this information, it should be clear to see that DRAM is more dense, meaning you can have fewer transistors implement just 1 bit of storage element. It takes very little area to use to create DRAM memory as compared to SRAM memory, which uses 6 transistors. So this is more dense compared to SRAM, which is less dense. Okay, therefore, it may seem that it is cheaper to have DRAM, but there is no free lunch. There's going to be more disadvantages for one versus the other. The choice between SRAM and DRAM is not solely based on the idea of density. Okay, there are other considerations like speed, storage permanence, so on and so forth. It seems there is something in the chat window. If one of you could go through what's on there in the DRAM, fewer components per cell. Jeff Harton has the right answer. DRAM is more dense compared to SRAM. That is correct. And in this class, we are going to compare and contrast the two topologies, okay, and see how to store a 1 or 0 into these memory cells. Okay, all of this we did in the last class. Okay, large area per 1 bit. This is lower area per 1 bit. So this is more dense compared to SRAM, which is less dense. Okay, so when I say density, I imply how many bits per millimeter square. Okay, so this is what we did in the last class. Okay, then I also talked about the idea of using memory components, okay, memory array to implement a lookup table. So let's follow up on that. Let's continue on that. I'm going to do this memory. Okay. So we are going to continue with the idea of using memory to implement a lookup table, or in other words, any combinational logic. Okay, let's say I have a memory that looks like this. Okay, a 4x4 memory. Okay, there are 4 rows, and I mentioned in the last class, the rows represent the address lines. So in other words, I can represent this row. I can represent this row using a digital code 00. This row represents 01. This row represents 10, and this represents 11. Okay, so horizontal lines can be uh, address lines. The vertical lines are data lines. Okay, so what I have done in the last class was to do this. See what happens if I write a value of 0, 0, 0, 1 into this. I mentioned that this particular column, okay, this column with the 0, 0, 0, 1 stored into these memory locations. These are all memory locations, right? So this represents AND gate. Okay, because if you look at the truth table of the AND gate of 2 inputs, okay, the truth table for AND gate looks like so. So what I have done is this component I have saved in the memory, okay, and these components I applied them as address signals. Okay, so by applying, let's say, an address signal of 1, 1, okay, the column corresponding to that comes up. So when I apply an address of 1, 1 and see, an output of 1, when I apply an input of 0, 0 as address and see an output of 0, and the corresponding truth table here being replicated, that represents AND gate. Okay, so what I can do the exact same thing for any combinational logic. So this is AND gate. It's for OR gate, I can do the exact same thing. What I do is I take the output value, I take the output, okay, so this guy, and store it in memory location. Okay, so I'm going to write 0, 1, 1, 1. And this guy, the address lines are applied as the, or the inputs are applied as the address lines. Okay, when I do that, what happens is I implement a lookup table for the OR gate. Okay, so that's the idea. We can implement any combinational logic using this guy. Okay, let's say any combinational logic of 2 inputs. Okay, I can implement any combinational logic of 2 inputs using a 4x4 memory. Okay, so let's see, what if I wanted to do, let's duplicate this. Sorry. So let me try to copy this here. Okay, and I try to implement. Okay, let's see what happens here. Let's say I have a memory cell that looks like this, a 4x4 memory block. And I want to implement a function that looks like this, that has not 2 inputs, but 3 inputs. Okay, how would I go about doing that? How can I go about doing that? Okay, how do you think I can modify this? Let's say I can use more than one of these blocks. I can use more than one of these blocks and any other logic circuit that you want to implement. Okay, so the idea is I have a 4x4 block. Let's say I have more than 4x4 blocks. I have two of those 4x4 blocks. Okay, I have two of these 4x4 blocks at my disposal, and I want to use them to implement a lookup table. Okay, the way I do that is by using a multiplexer. Okay, I use a multiplexer. The output from this is going to drive one input of the multiplexer. The output from this guy is going to drive another input of the multiplexer. So this is a 2x1 mux. So what I'm going to do is I'm going to break the entirety of this truth table into two blocks. Okay, I'm going to break this truth table into two blocks like so. And I'm trying to write the implement the AND gate. Okay, so what I do is this corresponds to a value of A is 0 here. Okay, and then I'm going to look at the next half, okay, which corresponds to an A value of 1. So the way I'm going to use this truth table is to write this part of the output into the logic, into the memory block over there. And I'm going to write this block of the memory output 0001 into the memory here. Then the address lines are going to be B and C, right? So the address lines is going to be 0001 1011 corresponding to B and C. The same here, the address line for this guy is going to be 0001 1011 corresponding to B and C. So what I have done is I'm going to take this B and C and apply them as address lines here. Okay, now what am I going to do with the third input that I have available here? Okay, the third input that I have available here, C, I'm going to apply that as the select line A. I'm sorry, I want to apply that as the select line. When the value of A is 0, the upper part of the truth table is going to be recalled as the output. Okay, when the value of A is 1, the lower half of the truth table is going to be applied. So let me color code them a little bit here. So this part represents A is 1, and the upper part represents A is 0. Okay, does that make sense? So the idea is I can use a combination of 4x4 memory to implement any combinational logic of 3 inputs. Okay, uh, I need to use 2 of these memory blocks to implement any combinational logic. Okay, all you have to do is take the output column, write it into the respective upper half and the lower half of the memory blocks, and then the 2 inputs are going to form the address lines here. And the third input, it does not matter if you choose these two as a pair. If you want to choose these two as a pair, you can rearrange C in a manner to represent zeros and one of C inputs. So you group B and C together, you applied them as the address line. The third remaining input A is applied as the select line here. So you have implemented a lookup table, okay, of 3 inputs. Of course, what we have to realize is that there is some extra space left over here that can be used to implement more logic. Okay, this extra space, this extra 3 columns that are available can be used to represent more additional functionality, right? So if you count here, I have 1 function AND gate and 3 more empty columns. So I can implement a total of 4 combinational logic functions of 3 variables. So 3 variable combinational logics, 4 of those can be implemented using a 8 by 4 memory. Okay, that's the idea of lookup tables. Questions, please. Questions so far. Okay, so what I'm going to do is I'm going to ask a volunteer to help me keep an eye on the chat window.
I can do it.
Thank you. I appreciate it. Now, while we are at it, let's talk about the idea of using multiplexers as well. So I trust that you get the idea of using memory as lookup table to implement any combinational logic. Okay? That's the idea. Now, what we can do is, as a matter of fact, use multiplexers as well. And I'm not going to spend a lot of time on this. I welcome you to look at this, okay? Let's say I have a multiplexer. Let's say I have a multiplexer, 4-to-1 mux. Okay, let's say I have a 4-to-1 mux with 2 select lines. Okay, I'm going to show you that this mux can be used to implement any combinational logic of 2 inputs or 2 variables. Let's say I have 2 variables A, B, and I want to implement the OR of those 2. Okay, so the OR of those 2, as you know, could have a combination of 0, 0, 0, 1, 1, 0, or 1, 1. Okay, that's the truth table part of it, 0, 0, 0, 1, 1, 0, 1, 1. That's the truth table. Okay, the output corresponds to 0, 1, 1, 1, which is the OR gate, right? So what I'm going to do is, just like we took one part of the truth table, the input lines, and applied that as the address lines, we're going to do something very similar here as well. We're going to apply the input bits as the select lines, and then the output, we're going to write it as the inputs to the multiplexer. And this in effect represents a OR gate. Okay, a multiplexer can be used to implement OR gate or any combinational logic. Okay, so what I'm going to tell you is, using a multiplexer 4 to 1, okay, with 4 inputs, 1 data output, and 2 select outputs, 2 select lines. I mentioned that it is possible to implement 2 variable combinational logic. Okay, 2 variable combinational logic, A, B. If you want to implement AND gate, 0, 0, 0, 1, 1, 0, 1, 1. So all you have to do is write the corresponding output column to that. Okay, that said, what I'm going to leave you with as an exercise is using a 4 to 1 mux to implement a 3 variable combinational logic. Okay, how can you use a multiplexer, okay, to implement a combinational logic, a 4 to 1 mux to implement a 3 variable? Obviously, what you have to do is you have to apply 2 of the inputs here and 1 of the inputs probably on this, okay, somewhere in here. So that part I leave as an exercise for you. Okay, how can you implement, or in the exam, I may give you a 4 to 1 mux. I'll give you a function that looks like this. Let's say I give you a function that looks like so. Okay, x1. X1 is ABC plus AB naught C plus A naught B naught C naught. Okay, implement that using four to one mux. Okay, if I ask you to implement this using 8 to 1 mux, that's easy, right? If I gave you a multiplexer of 8 inputs, 8 to 1 mux, okay, with 3 select lines. The select lines are A, B, C, okay, and then the input lines are, there are 8 of those input lines, okay, one corresponding to each possible combination of the inputs, the select lines, right? So corresponding to these, there can be all the values from 0, 0, 0, so on and so forth, okay? So on and so forth. All we have to do here in order to implement this functionality is to look at A, B, C values. So A, B, C is 1, 1, 1. That guy is a 1. A naught, B naught, C naught is 0, 0, 0. So that guy is a 1. A, B naught, C. So 1, 0, 1. 1, 0, 1. This is 1, 1, 0. So this guy is a 1. And the rest are all zeros. If I do that, then the corresponding output is going to be this guy, x1. Okay, so you can implement this using 8 to 1 mux. So my question is, it's easy to do that. All of this is nothing but the truth table output, and this is nothing but the inputs corresponding the input variables. Okay, so this is a different representation of the truth table itself. My question is, how can you implement this using a 4 to 1 mux? So you probably will have to shift one of these inputs onto the input of the mux itself, from the select to the input. Okay, it doesn't matter which one you choose. Okay, there's a method to how you can implement that. That is the gap I want to leave. That is the gap I want you to explore. Okay, questions, please. Okay. So how do you implement a 3 variable combinational logic using 4 to 1 mux? Okay, that said, let's move on to talking about the memories. Okay, the SRAM and DRAM memories. So as you know, memory is also called array subsystems. Because there is just one basic building block that is multiplied over and over like an array. Okay, memory forms the majority of transistors in a CMOS system on chip. There are different family trees that we looked at. Okay, and then there is random access, volatile versus non-volatile. There is volatile versus non-volatile memories. Even in volatile memories, there are two kinds. Okay, there is SRAM and there is DRAM. Okay, SRAM and DRAM, like we discussed. And some of the themes that we discussed about static and dynamic still apply here. If you remember, let me go back and see if I still have that in my old notes. I'm going back to my old notes here from the last class, okay, where I tried to, maybe I did not. So I tried to point that combinational logic had a static and dynamic aspect to it. Sequential logic, the different latches that we looked at were static or dynamic themselves. Memory is also static and dynamic. Okay, so with that, let me revise some of the idea of static and dynamic. One of these has feedback. Okay, this guy has static RAM always has feedback, just like static latches, which had feedback. Dynamic RAM, on the other hand, has no feedback. Okay, there is a cross-coupled pair of inverters. Inverters tied in a cross-coupled back-to-back fashion. Okay, that reinforces. Did we see this architecture somewhere? Where did we see this architecture? Did we come across this idea of a feedback reinforcing, staticizing some of the
in
sequential
the
circuit?
delay, the latches. Yeah.
In the latches, thank you. When we were looking at static versus dynamic latch, okay, the dynamic latch had just one capacitance, okay, that was driven by an inverter, okay, that was dynamic, okay. But when we incorporated a feedback, a back-to-back connection of inverters, it is a staticized latch. We staticized the latch by incorporating a feedback. So the same theme here as well. Static RAM also has feedback, okay, to reinforce data. DRAM, dynamic RAM, on the other hand, relies on storing the value 1 or 0 on a floating cap. Okay, this idea of floating cap has been familiar to us even from dynamic logic circuits, where the capacitance was a leaky bucket or leaky balloon that gradually kept leaking charge. Okay, the same exact problem here, a leaky cap, means that you have to keep refreshing. Okay, so for example, if I write a 1 on this, that turns out to be, that gets inverted to be a 0. And this 0 is again reinforced to be a 1 via this feedback loop. So whatever capacitance is holding data here, or we don't even need a capacitance, whatever, this forms the basic storage element. As long as power is supplied to this, the contents of this memory keep reinforcing themselves. Once the power is turned off, the contents of the memory are erased. It's volatile memory, basically, right? So the idea that one gets inverted to a zero and zero gets inverted back to a one, reinforcing itself as long as the power is constantly provided, is the idea of volatile. But look at this guy. Even when I write a value of 1 to this, even when the power is being supplied, owing to the fact that this capacitance is leaky, it tends towards zero. So I need to refresh the contents again. I need to keep rewriting this one over and over and over again, multiple times, even with the power on. So this needs to be refreshed because the idea that the capacitance is always leaky because of that. Okay, so even though this guy is less dense compared to this guy, which is more dense because it uses fewer transistors, as you can see, there are two inverters. Each inverter has two transistors in them. So there is at least 4 transistors. And then in addition to that, I need 2 MOSFETs to access the storage. Okay, and I'm going to talk about how and why they are necessary. Okay, so we are building from ground up the idea of SRAM and DRAM. Okay. So all of these apparatus, 6 transistors are necessary to hold 1 bit of data, while there is only one transistor, and 1 cap, which can also be implemented using a transistor, using DRAM. So this is more dense, and this is less dense. So even though there is a disparity in terms of density, when it comes to operation, DRAM is less efficient. SRAM is quicker, SRAM is fast, SRAM is more efficient. Okay, more, but it is SRAM is more dense than flip-flops, but it is less dense than DRAMs. Okay, it's less dense than DRAMs, the SRAM itself. Okay, it's denser than flip-flops. Compatible with standard CMOS logic. It's faster than DRAM. It's easier to use because you don't need to refresh this. So it's expensive compared to DRAM, which is less expensive, which is cheap. And then it is used in cache, registers, okay, scratchpad buffers, tables, so on and so forth. It's used in applications where you need to operate the memory at a very fast, pace compared to DRAM. Okay, so let's take a closer look at the SRAM cell. So questions so far, please. Like I mentioned, fundamentally, there is a cross-coupled inverter pair. So based off of that, let's see how the transistor inside looks. Okay, so this guy, the inverter here, the first inverter is this guy. There is a PMOS, there is NMOS. Okay, so that's one inverter. There's another inverter pair here. We are looking at the internal connection of SRAM cell that uses 6 transistors. Okay. So now just like this guy, the input of one is connected to the output of the other. Okay. Even so, the output of this guy is connected to the input of this guy. Okay. So that's exactly what I'm doing here. The input of this transistor here is connected to the output of this guy. Okay, so let me do this. The input is connected there, and then the output of one is connected to the input of the other.
There's a question in the chat.
Can you read
Kyle
it out?
asks, oh, couldn't. Okay, sorry. So Kyle asks, why is SRAM faster than DRAM if it has more transistors?
The idea is that when we are using this capacitance, in order to the support circuitry that is necessary to keep refreshing the DRAM, that slows it down. The capacitance slows it down further. And then the operating current on these transistors is high enough that it keeps them fast. Okay. So because of the involved capacitance and because of the support circuitry that slows down the DRAM, because of these two reasons, the DRAM is slower than SRAM. Okay, so there are 4 transistors here, 2 inverters connected back to back. And in addition, let's say there are 2 more transistors. There are 2 more transistors. These are called access transistors. Okay, and I'm going to extend this guy over here. Okay, there are 2 transistors that are called access transistors. Okay, and then they are driven by a separate line. Okay, they're driven by a separate line. And what is of importance to me is this bit. Let me do it using a very thick line, is using this bit. Okay, and big bar. Okay, so that represents access to this guy and this guy. Okay, so what I have not shown here is the access, oops, I have not shown the access transistors here. Okay, let's see. That's the cross-coupled inverter. So this is called the bit line. This is called the bit bar line. Bit bar. Okay. So if this represents the 0, naturally this represents a 1, and vice versa. If this represents the one on the left represents a 1, this represents a 0. Okay, so I stored both 1 and 0, 1 bit of information over here. And this guy is called the word line. Oops. Okay, on the bit and bit bar is my data. Okay, and the data complement. This is the storage. Okay, so for this one cell of memory, so if I go back, these 6 transistors, and if I were to do this, okay, this block of memory is what is sitting inside each of these cells here. Okay, so if you zoom into each of these cells, each of those is comprised of 6 transistors. Then that guy is called SRAM. Okay, if instead you use 2 of the DRAM components, it becomes a DRAM array. Okay, so now that's the idea here. So questions so far, please. So the transistors are called, let's see, access transistors. Okay, and then just give me 1 second while I get the naming for these exactly right. Okay, want to get the naming exactly right for this. There are a bunch of transistors, 6 transistors here, and that is important because their relative sizes matter. There are 2 PMOS transistors on the top, 2 NMOS transistors on the bottom. Okay, and The access transistors shown in purple, both of these are, both of the purple transistors are NMOS transistors, okay? So let me see, array subsystems, SRAM. Okay, this is called P1, PMOS one. This is called P2. Okay, this is called access transistor 1. This is called access transistor 2. The one down below are D1 and D2. Okay, so with these transistors, it's easy to identify how to size them carefully. Okay, so there are two operations here. First of all, there is no data that is being currently stored in here. Okay, so what I'm going to do is I'm going to maybe make all of these. Okay, there's no data that is currently being stored here. Let us say I want to read, or let's say this data is sitting in here. Let's say I have written a value of 1 onto this and 0 onto this. Okay, so this node holds a value of 0 and this node holds a value of 1. Okay, so this holds a value of 0. Okay, and this holds a value, oops, this holds a value of 1. Okay, what I want to do is to read this data onto the data lines. So this storage memory, I want to copy onto the data lines. That's called the read operation. So there are two operations here. There is a data read operation, and then there is a data write operation. So if I want to copy the values of this storage, the middle component, onto the bit lines, I should pay attention to the fact that I don't want to overwrite accidentally. Overwrite what is available, what is already sitting here, okay? Or corrupt the storage. Okay, so in other words, when I'm making an effort to read the value of these contents, read the value of these cells onto the bit lines here, I should be careful not to disrupt the memory contents itself. Okay, so the way I do it is the read operation here is what we do is, first of all, we make the word line 0. Okay, we make the word line 0. When the word line is 0, what happens is this PMOS, this NMOS, and this NMOS are turned off. Okay, so in other words, both of these are floating. There is no connection made to the data lines. Then I put a value of 1 floating. Okay, I pre-charge them. Okay, or pre-charge. Okay, I'm not driving them. Okay, what we want to do is understand is that we are floating them high. We charge them to a value of 1 and then take the power supply off. We don't make a continuous connection to the power supply. So both of these lines, bit and bit bar, shown here, are pre-charged to 1 and left floating. Then what happens is, then in the next cycle, the word value becomes 1. Okay, when I make the word value 1, this access transistor turns on and this access transistor turns on. Okay, both of these NMOS transistors turn on. So this 0 is going to be, let's see, let me show it using here. This 0 is going to connect to the bit line over here, which is already carrying a 1. Okay, so what I want to do is that I want to discharge this 1 to a 0 because there is a connection to the ground here. Okay, that is what I want to do. Then on the other side, what I want to do on the other side is I want to write this value of 1. I want to copy this 1 and reinforce what is already sitting here through this power supply, positive power supply. Okay, so through the access transistor A1, okay, does that make sense? Through the access transistor A1, I'm making the bit line. So the bit line is going to be reinforced to a value of 1, and bit bar is going to be pulled down to a 0. Okay, does that make sense? So questions, please. What questions do you have when it comes to reading operation? Reading operation is that I'm trying to mirror this value, the contents of this memory from here onto the data lines. Okay, so this 0 should reflect or mirror onto the bit and bit bar lines. So that way I have read the contents of this memory without accidentally corrupting the storage. Okay, what do you see as a problem here or something that I have to pay attention to? What do you think happens? Okay, what do you think happens if this 1 that was left floating is very strong? If this 1 is strong, when the word becomes 1 and the purple path is established, what happens is instead of discharging to 0, what it does is this 1 corrupts the contents and makes a 0 to corrupt to a 1. Okay, so when we are reading, we should be careful not to corrupt the contents, not to disturb or overwrite the contents inadvertently. Okay, when we make the connection through A2, I want to be really sure that there is only discharge happening in this path. Okay, the way to make sure that this is happening is um, by having relative sizes of D2 and A2. And I will talk about how to size them properly. Okay, so what you have to do is that the discharge path is stronger. D2 is stronger than the access transistor A2. Okay, but there is a danger if you don't pay attention that when we are trying to read the value from the memory back into the data lines, because of the way we float this to be a high, that could in fact reflect as a 1 over here, corrupting the contents, which we don't want. Okay, so this is the idea of read operation. Does that make sense? Okay, so what we are doing is a read operation here. Okay, let's see how we can do a write operation. Okay, a write operation for the exact same cell. Okay, let's get rid of all of this coloration here. So write operation on the memory cell. Okay, let's say the initial contents, let's say the word is, I don't know, let's say the initial contents are 1, okay? Initially the contents are 1 and 0 inside the storage component, inside the memory part of it, okay? And then the data are to the left and the right, okay? So in order, earlier, the condition was that during read operation, okay, we want to make sure that the inverters are stronger during read operation. So right here, during read operation, the inverters, especially the D1 and D2 are stronger than access 1 and access 2 transistors. We want to make sure that D1 is stronger than access 1 and access 2 transistors. So for read stability, okay, we want to ensure that D1 is greater than A1. Okay, so in other words, D1, the size of this NMOS transistor D1 is larger than the size of the access transistor A1. Okay, that's the idea. So for writability, what we have to do is, so in other words, so that's the idea. So the reading operation is shown over earlier. Now the writing operation, the writing to SRAM happens in this fashion. Okay, let us say I want to overwrite the contents here. Okay, initially I have a 1 and 0 sitting. What I want to do is I want to write a value of 0. Okay, I want to overwrite a value of 0 onto this and a value of 1 onto this. Okay, let's say that is happening. Let's say that's what we want to do. In order to do that, what we do is we try to write a value of 0, pull this value 0, and we leave this at 1. Okay, so the bit and bit bar lines, what happens is there is a drive buffer over this. So this guy is connected to a drive buffer. I'm sorry, we have to do the opposite, right? We are trying to put a 0 on here. So we leave this at 0 and we make this a 1 and make the drive buffer drive the opposite of what I'm trying to put here. So if I'm trying to put a 0 here, then I will write a 1 onto this drive buffer. Okay, and I'll put a 0 on the right. So initially, and then make the value of word equals to 1. Okay, when the value of word is equals to 1, this PMOS transistor, this NMOS transistor turns on. This NMOS transistor turns on as well. So what you want to do is you want to make sure that this 0 is eventually written to a 1. Okay, so for this node to charge to a 1, it should happen through the PMOS transistor. Okay, so you ensure that P2 is stronger than A2. So this is called writability. The PMOS transistors, P1 should be stronger than A1, okay, for writability. And then the NMOS transistors, D1 and D2, should be stronger than A1 for read stability. So this condition is called read stability. And the condition over here is called writability. Okay, the access transistors, NMOS transistors, so on and so forth. Or should I, let's say, okay, maybe I have this backwards. The idea should be that A1, sorry, I'm sorry, A1 should be stronger than D1. A2 should be stronger than D2. Okay, so that's the idea. And I'll give you a generic rule for, so the idea of write operation is, so let me summarize the write operation. We can make the word line equals to 0 first. Okay, then bit takes the desired value. Okay, bit bar takes the desired value complement. Okay, and you drive this value using the write buffer or the drive buffer. Then you make the word line equals to 1. Then what happens is the 1 here overpowers what was initially sitting over there, is 0, and then replicates, mirrors itself from the data line into the memory here. Okay, so the read operation is opposite. You're trying to mirror it in that direction. Okay, the read operation is mirroring it in this direction from the data lines into the memory. Okay, questions please. Questions so far? So in effect, the read stability and the writability together mean that the PMOS, NMOS transistors, pull down transistors, should be stronger than the access transistors, which should be stronger than the PMOS transistors. Okay, should be stronger than the PMOS transistors. A2 should be stronger than A1 should be. So I have it backwards. Okay. So in effect, the idea is NMOS transistor is larger than the access transistors. So D1 and D2 are size larger than A1 and A2, and then which are in fact in turn stronger than P1 and P2. Okay, so questions please, questions so far. Okay, so this is the idea of read and write operation. Okay, read and write operation. Let me summarize the SRAM. Read operation is both bit and bit bar are pre-charged to 1 and left floating. And they're floated. Okay, they're left to float. Okay, and then so word was initially 0, or the access was initially 0, and then the word turns on now. That's the idea of read operation. When it comes to write operation, okay, bit and bit bar, okay, you put the desired value here and the desired value complement over here. Okay, this is floated, this is driven. Okay, this is driven. Then what happens is word becomes 1. Initially word was 0. Okay, so when that happens, the value is written, and then by ensuring that the NMOS transistors are larger size than the access transistors, in turn larger than the PMOS transistors, we ensure read stability and writability. Okay, so that's the idea of writing and reading from a reading and writing from Sram, sir. Questions, please. Questions so far.
Dr. Mituri,
Yes.
it wasn't clear how you can control when you want to write versus when you want to read.
Yeah. So really what happens is, let's say you want to, let me draw this. Let me see. Read versus write. Okay. There are control signals that assert whether you want to read or write. But at the base core level, okay, at the cell level, this is what is going to happen. Okay. So Lillian, it was you who had this nice question, right?
Yes.
Okay. Now tell me, for our example, do you want to first read or write?
I would like us to write.
You'd like to write, okay? Let's say I have a value of a 0 that is initially sitting in here. That means a 1 is held over here, which reinforces through the pair of transistors. Okay, so your question is, it is not really clear whether I'm trying to read or write. So when you want to write, let us say for our argument's sake, I want to write a value, overwrite this with 1. That means I should write a value of 0 in here. Okay, so when it comes to the write operation, the fundamental difference compared to a read operation is that you put a value of 1, you pre-charge this node, bit node to 1, and you put a value of 0 and drive it. 0. When you drive the bit bar line to 0, not float. So this guy is floating, but this guy is driving. Okay, so in other words, what you do is the difference between floating and driving is when you charge a capacitance to VDD and leave it floating, then that is floating. Instead, if you charge it to ground or connect it to a power supply, that is driving. Okay, so without getting too lost in a maze of words here, the idea is when you float and drive, that's a read operation. On the other hand, when you float and float, it's a read operation. So float and float is read, float and drive, okay, that's right. Does that make sense?
Yes, it does. Thank you very much, Dr. Mituri.
Yes. Okay, that's a good question. Okay, what it means to be floating is to pre-charge it and disconnect the power supply. When you're driving it, you pre-charge it, but you still leave the connection to power supply intact. You don't disconnect from the power supply. Okay. You want to see, the idea is you want to drive this guy, because it has to overpower what is already sitting in there. So in order to do that, it needs a continuous connection to the lower power supply, because I'm trying to drive a value 0 in here. Okay, so instead of that, if I leave it floating, that becomes a read operation. Other questions, please? All right, we'll stop here. We'll come back on Thursday and continue with a few other. Let me see something in the chat window. The bit line is the value that we actually are reading when we are reading into the memory. That is correct. When we are reading the value on the bit line. Okay, so bit line is what we read. So Daniel Comac had this question. Okay, we are actually reading the value from the bit line. Okay, we'll stop here and then we'll come back and discuss in the next class.